Adam optimization. Adam is one of the most widely used optimizers in deep learning, combining momentum and adaptive learning rates. So in the previous videos, I have talked about SGD or stochastic gradient descent, momentum, AdaGrad, RMSProp, all these optimization algorithms. So I highly suggest please go through those earlier videos to understand this, but I'll just give a quick recap here. So I'll quickly talk about what these optimizers are about and what this lacks. So SGD or stochastic gradient descent, it updates weights using a single or mini batch sample. So if we have a huge data set, it divides the data set into multiple small batches, and one iteration is only for one mini batch. So this is somehow one optimization you can say. But the problem with SGD is we still have slow and noisy zigzag weight updates, and it can get stuck in local minima or saddle points. If we talk about momentum, momentum is it is based on the direction of the change. So if we have this loss curve like that, and let's say if you are moving in this direction, right? So for multiple few times, if you are moving in the same direction, then you will take larger step in that direction. So multiple updates in similar direction means larger step in that direction will take. So momentum is great, but it doesn't have adaptive learning rate. What is adaptive learning rate? So our gradient descent update is something like this, right? WT plus 1 is WT minus alpha, this gradient of the error function, right? So this is the vanilla gradient descent, but what happens, this error function, the gradient of this error function, it is something like this, right? Del E, del W11, del E, del W12 and so on. Like for multiple weights, we'll have multiple this gradient components. So, but here you are using this alpha as a learning rate. So all the gradient components are having gradient weights as having the same learning rate. So we don't have adaptive learning rates. So that is the problem we are trying to solve in AdaGrad. AdaGrad has adaptive learning rates. So the weight parameters that is having these weight parameters which are having rare updates, those will have larger learning rates, and those are having like frequent updates, those will have smaller learning rates. AdaGrad solved a great problem, but still it has one minor problem, that is the aggressive decay problem. So the learning rate can become negligibly small, causing training to stall prematurely. So sometimes for features which are getting updated multiple times, for those the learning rate can become very small, like close to zero. So that is the problem RMSProp is solving. It prevents this learning rate from vanishing. But RMSProp doesn't have this momentum approach, right? So it is not considering the direction of the change. So while it is adaptive, it lacks the velocity found in momentum. So now next comes this Adam. So that is basically, it will take all the benefits, all the positive points from all the previous optimizers, and it will combine all this. So mainly Adam will combine momentum and RMSProp. So RMSProp is basically one improved version of AdaGrad, right? So if we combine momentum and RMSProp, we are good. So momentum will give smooth direction. RMSProp, it will give the adaptive step size or adaptive learning rates. Now I'll just give a quick recap of momentum and RMSProp. In momentum, we have this velocity or gradient accumulated. So this Vt plus 1 is beta time Vt plus 1 minus beta time this gradient at this previous t iteration. So momentum has a simpler version also, like Vt plus 1 is Vt plus gradient, right? So it's basically accumulating the gradients in each iteration. So it's kind of a cumulative sum. So this version, this is an improved version of momentum where we are using convex combination. It is just to have a bounded value, limited value for this gradient accumulator. So this Vt plus 1 or Vt, this is the velocity or gradient accumulator. We are using convex combination of past Vt and current gradient, and that's why we call it exponential moving average of gradients. So this is momentum. It is focusing on the direction of the change. So this gradients, this will have all the components in the gradients will have different directions, right? So it is focusing on those directions. In RMSProp, what we are doing, we are taking one accumulator. So this is one RMSProp accumulator. This is the squared gradient accumulator. In momentum, we just considered gradient. Here we are considering dot product, element wise dot product of the gradients. So the signs or the directions we are ignoring. We are just considering, we are just focusing on the magnitude of the change. And this is also one convex combination approach. We are just like taking, this is a squared gradient accumulator with convex combination. So instead of one, and what is this doing? The main improvement in RMSProp is this word. So earlier we just had in vanilla gradient descent, we had this, right? Wt minus alpha times the gradient. So here, instead of just the simple alpha, so we have alpha divided by this term. So this is one vector. So 1 over delta plus RT plus 1. So this is one vector. So what we are getting is alpha time this thing. So this is a vector. Why it is a vector? This RT plus 1 or this is also a vector. Gradients are vector, and all this RT is, this is also a vector. So what we are getting here is this one element wise dot product with the gradient. So different weight parameters in this gradient will have different learning rate. So that's the improvement. So weights with rare updates will have higher learning rate, and weights with frequent updates will get smaller learning rate. So it prevents the learning rate from vanishing. As this RT plus 1, here we are using convex combination. So without convex combination also we have one version, that is the ADAGRAD, but here we are using convex combination. So this is one exponentially weighted moving average of squared gradients. So this is about RMSProp, and earlier we talked about momentum. Now we'll combine these two, and that will be our Adam formulation. So we have one accumulator. This is the velocity accumulator that is coming from momentum. This will track the direction, and then we have squared gradient accumulator. This will keep track of the magnitude of the change. This is coming from RMSProp. And then here we have the gradient update, gradient weight update. Wt plus 1 is Wt minus alpha by over del plus this root over square root of Rt plus 1 dot product of Vt plus 1. In normal plain RMSProp, we had this gradient here, right? So instead of that, we are using Vt plus 1 from the momentum. So this is the change. So this is how it is combining like momentum and RMSProp. So Adam tracks two moving average, like one for momentum, one for adaptive learning rate. So this one, the from momentum, it reduces oscillation, like focuses on direction, right? So it is reduces the oscillation. And one for adaptive learning rate, it controls the step size.